Good afternoon, everyone. Thank you for coming. Today we have a great pleasure to have John Murphy here from Warwick. So John did his PhD in Oxford University and then moved to Warwick. He leads a small team there. He's world expert in bulk defects, mainly oxygen precipitate. For me, it's always a celebration to read his paper. It's like always written very well, very interesting, very good description of the analyze. It's always something that you can learn. So I'm sure that most of you read his papers and probably you agree with me. So it will be a pleasure to hear his presentation, a bit of summary of what he did and what his group is doing now. So please welcome John.
Thank you. Okay, thank you. I'd like to first start by thanking Ziv and Darren for having me here for a few days. I'm around for the rest of today if anyone wants to see me afterwards. I'm going to talk about bulk lifetime issues in silicon for photovoltaics. But first, I would like to just mention the UK activity in this field. So I lead a small team in Warwick. We've also got activity in Manchester. Some of you may know the DLTS group there, led by Tony, and also Peter Wilshaw's group in Oxford. We got this big for us, UK grant working in this area last year. And we went internationally to recruit, and I'm pleased to say we recruited some excellent Australian scientists to the project. So currently we've got Phil Hamer working in Oxford, and Nick Grant, who was previously at ANU working with me in Warwick. So there's a strong Australian connection to the UK in this project. So I'm going to talk today about carrier lifetime issues in silicon PV. I normally start my UK seminars by giving an introduction to PV, saying why silicon's important, but as I'm at UNSW, I don't really think I need to go through the basics of this. So I'm going to go straight into some detailed stuff about lifetime issues. Clearly, we've had some great advances in surface passivation recently, and pleased to see Bram in the audience, and we heard from him in Oxford recently about that. But at the moment, there are quite a lot of bulk issues that are really affecting the conversion efficiency of solar cells. So that's the focus of this talk. It's bulk recombination processes. I'm going to start by talking about how we quantify lifetime, and the approach we're using developed in collaboration with Bob Forster and Vladimir Voronkov at Sun Edison to analyse lifetime data and to understand the physics and the mechanisms of recombination in silicon. So here's an overview of my talk. I'm going to start by talking about our approach to analyse injection-dependent lifetime data. I'm going to go on to talk about how we use it to study recombination at oxide precipitates and defects surrounding those. I'm then going to talk about something slightly different, about internal Gettering in multicrystalline silicon at low temperatures. And if time allows, I'm going to give a plug for Nick Grant's work on high lifetime materials for PV, but I may not get there with the time constraints of this seminar. I'd like to first start by thanking my co-workers. A lot of the work I'm presenting is done in collaboration, particularly with these guys, Bob Forster and Vladimir from Sun Edison, Karsten Bother at ISFH and Raphael Crane at ISFH, my own team at Warwick, Mohammed Al-Amin, Alex Poynton and Nick Grant now, Rachel Maguire at Oxford, and the people at ANU, Dan MacDonald and Fiac Ruggier in particular. Okay, so I'm sure that most of you are familiar with injection-dependent lifetime measurements. The synton-based measurement approach, you typically have a flash, some filters, a sample sits on top of an eddy current sensor, and you have a photodiode at the back to measure the generation rate when you're making a quasi-steady state measurement. This is the kind of approach that every PV lab in the world uses, and you typically measure a light intensity profile at the same time as measuring a conductance change, use some mobility function, and then you can calculate the minority carrier lifetime as a function of carrier injection level, delta N. And what people tend to do is acquire curves that look a bit like this. You've got lifetime here, the electron lifetime in p-type material as a function of the excess carrier concentration, delta N, and you plot lifetime as a function of delta N. And this is great, but it's not the most convenient way we find of showing the physics of the recombination process. So what we're trying to do is work out ways of visualizing recombination better. So if you instead, when you're doing a lifetime plot, rather than plotting lifetime against delta N, if you plot lifetime as a function of this parameter x, which is the total electron concentration to the total hole concentration, you get completely different behaviour. So these are the same data. The top data here is against delta n, the bottom data is against n over p, and you can see that this, what looks like a complicated lifetime curve at the top, is actually a very straightforward straight line at the bottom. So by going through this linear formulation of Shockley-Reed-Hall statistics, we can more easily visualise the physics of the recombination process. And for information, this is interstitial iron in silicon. This is a single defect in the material, produces a curve on the delta n, but a line in the n over p trace. And this approach is what we've used quite a lot in analysing recombination in bulk silicon materials. Now, the details of this are probably a bit dry, and I can better refer you to the paper on this, which is up here. But rather than using the Shockley-Reed-Hall expression, where you have the delta n terms here, the standard expression, you have delta n there, there, and there, you can write, and we show this in the paper, the lifetime in terms of two terms, this pre-term here and this term here, the second term, which depends on the injection. So what we do is we have the lifetime expression here as a linear function of x. You've got a set of variables here which are essentially a constant, independent of injection level, and the second term here has all the injection information in it. So you have all the delta n bits in the second bit of the lifetime expression. And this is great because it gives you a straight line for a single Shockley-Reed-Hall defect. And this is basic. It's quite basic, but I encourage you to try this if you're doing analysis of lifetime data, of just plotting lifetime rather than against delta n, but against this parameter n over p. And that will give you, potentially, if you've got a nicely behaved system, a way of visualising your lifetime properties better. So the neat thing about this approach is that it enables us quite straightforwardly to extract the defect parameters. And so this is the equation from the previous slide. It has a lifetime equaling some term which is independent of injection plus an injection bit multiplied by another term. And so a single Shockley-Reed-Hall defect gives you a straight line on this plot. The neat thing though is that you can use this really easily to extract the defect parameters of a system. So if you take the gradient of this line, so all we do is we take a lifetime measurement, plot it like this. If it's linear, we put a line through it, and we measure two things. We measure the gradient of this line, and we measure this high injection limit, where x equals 1, limit of the lifetime. And by doing this, we can extract very easily information on the recombination process. So if we take the gradient, divide it by the high lifetime limit, we get something of this form. So this is just using the equation, put x equals 1 into the equation, you get certain bits cancelling out, so you get the q and 1 over p naught cancelling with that bit, and this bit there cancels with that bit there, and you have a very simple expression for lifetime. And from a plot of these really simple to extract numbers from a lifetime curve, doing this at different doping levels, you can extract both the ratio of capture cross sections, which we call Q, which is the electron capture cross section to the hole capture cross section, and from the gradient of this plot we can extract information on the energy level. So what we've got here is a way of really easily extracting the physics of a recombination process from lifetime data. You also get from the x tends to 1 limit a term proportional to the state density. This might seem a bit dry, but I'll illustrate its use with an example. And one of the systems we've used it on is indium doped silicon. So you've probably, I'm sure everyone in the room is familiar with the idea of light-induced degradation. One of the problems, big problems in p-type silicon doped with boron is that it degrades under light. And it degrades under light due to the formation of a centre containing boron and oxygen. And many of you have worked on that here. We're investigating an alternative p-type dopant in our work, and this is indium. And this shows neatly how this injection analysis works. So here we've got two samples doped with indium. Now, the slightly complicated thing with indium is that the shallow level is rather deep, and so at room temperature it's not fully ionized. If you do a Hall effect measurement, you can work out the ionized indium concentration, which gives you the majority carrier concentration. Now, the rest of the indium, the indium that isn't ionized, acts as a recombination center. It's a deep level, and that gives you a certain recombination behavior. And so here you can see two injection-dependent lifetime curves. This is lifetime corrected for Auger and band-to-band recombination. This is N over P, as I showed earlier. And you can see that in this case, this is experimental data now, we see two straight lines for the different indium concentrations shown. And so just using this N over P approach shows you that you can actually get straight lines in this simple system, and you can do the analysis I talked about earlier to work out what the energy level of the defect is. So this is the same equation from earlier. We've got this term here that's independent of injection level, and the second term which is totally dependent on N over P. We can do this experiment for different values of P naught, and we can do this plot of just the gradient of the lines divided by the high lifetime limit, and you plot that as as a function of 1 over the doping level of the ionized indium concentration. And by doing that, you can work out just from minority carrier lifetime measurements, you can work out the energy level of the indium defect. And so this is that variable here. These are the experimentally measured values of the gradient over the high injection limit. And this is 1 over P naught, 1 over the majority carrier concentration at room temperature. And you can see you get a nice straight line on this plot. And just from simple maths, the gradient of this plot is given by Q N1 plus P1 over 1 plus Q. The intercept up here somewhere gives you Q. You can put the Q back in here, and you can get a value for the term Q N1 plus P1, and you can get a value for the capture cross-section ratio Q. So just by analysing simple lifetime data, you can get most of the physics that you can get from lifetime measurement out. And in this case for indium, you can get, well, you get Qn1 plus P1. You have to assume that the defect's close to the valence band. As it's a p-type dopant, that's okay. And you can therefore extract the energy level of the indium defect from the injection-dependent lifetime curve. And so this energy level turns out to be about 0.15 eV above the valence band. So that is very consistent with Hall effect measurements and optical measurements on indium-doped silicon. So I think this approach is very valuable in analysing lifetime data, and I encourage you to give it a go. There are a couple of more complicated cases. So until now, I've only had one defect in each system. You could have the situation, for example, where you have two defects. So here I've shown one defect, which is the iron-boron pair, another defect here, which is the interstitial iron defect. And if you engineered a system whereby both of those were independently in the material in the same concentration, you could combine their lifetimes in reciprocal like this. So you can add the recombination rates to get the overall recombination rate. So if you've got two independent Shockley-Reed Hall centres, all you have to do is add the reciprocal lifetimes together to get the reciprocal lifetime of the entire system. And this is what it looks like here. More complicated case, and this was used recently by Tim Niewelt at Fraunhofer ISA in analysing the boron-oxygen light-induced degradation. This is a more complicated expression for the lifetime injection dependence for one defect with two energy levels. And so this is what Tim used in the analysis published recently. Okay, so what we've got here, the first part of the talk was to say that we have an approach which I encourage you to give a go to if you haven't already for analysing lifetime data in any type of silicon. It works in p-type and n-type. The key point though is that you can get a lot of the physics of the recombination process out by merely analysing the injection dependence. The key points are that you can't get the physics out from just one lifetime measurement. That doesn't tell you very much about the recombination mechanism. But if you can do your experiment with different doping levels and you can vary the majority carrier concentration, you can easily get the information out on the physics of the recombination mechanism from analysing the injection dependence as I said. Now, there are some limitations to this, but the limitations are there in any form of lifetime measurement. You can never get out the state density in isolation, because if you look at the equations, the state density is always coupled to one of the capture cross sections. So you can only ever get a term proportional to the state density, but you can quite easily get information on the energy level and the ratio of capture cross sections. So I'm happy to talk to anyone afterwards about this approach. If you're interested in it, I can show you the details of how to do it. I'm going to talk now, for the next part of the talk, about how we use this in studying recombination at extended defects in silicon for PV. So we've done a lot of work on oxygen in silicon. And as I said earlier, I'm sure a lot of you have worked on boron oxygen light-induced degradation. There is another form of oxygen-related defect in silicon which has a detrimental effect, but more stable, on the lifetime. And that's the formation of oxygen-related extended defects. So this is a phase diagram for oxygen and silicon. This is temperature. Now you can see that actually the equilibrium phase for the silicon-oxygen system, at most processing temperatures used for PV, and for most typical oxygen concentrations of around 10 to the 18, the equilibrium phase is the silicon plus SiO2. So thermodynamically, there is a driving force to have oxygen precipitation in the material. Now, in silicon for integrated circuits, this isn't really an issue, because you grow the crystals to be very high quality, and you can optimize the intrinsic point defect concentration so that you don't have any nucleation centers for these precipitates. In PV materials, you pull the crystals very quickly, and so you get what's called, what we refer to as suboptimal V over G ratio. The growth velocity to the thermal gradient at the growth interface isn't optimized for the lowest intrinsic point defect concentration. And so typically what happens in PV materials is you've got lots of potential nucleation centers forming in ring-like structures around the wafer. And these nucleation centers are where the oxygen precipitates. And I'll show on the next slide an image of what typically results from oxygen precipitation in silicon. So this is an image from Fraunhofer-ISA. You can see this is a PV wafer, and you get these characteristic ring-like structures. Now, this is all well understood. Vladimir Voronkov did a lot of work in this in the early 80s. These rings are probably rings of vacancies. At those vacancies, you get oxygen precipitation. Remember, that's the thermodynamically stable phase. And you get these rings of oxygen precipitate-like defects, and you therefore have recombination activity at those. You also find in silicon, in multi, that you get oxygen-related precipitates forming. In this case, I think at a grain boundary. In this case here, we've got co-precipitation of metals and oxygen. But oxygen precipitates form in silicon PV. Now, to understand this properly, we have to understand how the oxide precipitates actually grow. And this is a very complicated process, but it is understood. So what happens, it's a four-stage growth process. Initially, oxygen clusters and forms these unstrained precipitates. And we know that this happens because we can measure the IR loss of oxygen from the bulk. We know that the oxygen's going somewhere. We know it's not leaving the material because we can do a reversible process and we can get it back again. But we know that oxygen's being lost from the bulk. So initially, oxygen clusters together and forms unstrained precipitates. They can't be seen. And suddenly, they pop out and become strained precipitates when they can be seen. So we go from a transition from an unstrained to a strained precipitate. And because they jump out at you, I think the guys at Sun Edison call these ninja particles. They suddenly appear. They were always there, but suddenly they transition from being undetectable to detectable. And that is good from an IC point of view because they become Gettering active. They can trap metallic impurities better because they've got more strain around them. It's probably bad from a PV point of view, because they act as stronger recombination centres than the unstrained precipitates. And then as oxygen precipitates grow further, they get bigger. So we go from a 50 nanometer roughly precipitate here to a 500 nanometer precipitate. And then what happens after more processing time is that they start popping out some dislocation loops. And if you anneal them a lot, you get oxygen precipitates surrounded by stacking faults, these beautiful stacking faults forming around the precipitates here. And so we have to understand this process when understanding the lifetime in the material. Now for IC material, it turns out that these precipitates here, once they're strained and they have dislocations, they're actually good because they attract metallic impurities and they get them away from the device. But for PV, that's bad. And so we have to understand this recombination, this mechanism in terms of the recombination activity. So what we did, this is about 5 years worth of work. We grew a lot of precipitates in a lot of samples. I think probably more than 100 now samples, different types, different P-type, N-type, different oxygen concentrations, different doping levels. We used different growth conditions. But typically what we did is here, we did a 4-stage precipitate growth treatment. So we first of all wipe the material clean. This is really important because during crystal growth, you do get small nuclei of oxygen precipitates or nanoprecipitates forming. So we have to wipe the material clean. So we start with a 15-minute anneal at 1,000 degrees C. That dissolves any potential nuclei, called a tabula rasa process. We then deliberately nucleate precipitates. We choose a low temperature to do the nucleation. And then we do quite a complicated thermal process to grow the nuclei gently, and then we do a big growth process at high temperature for different times. So we can vary the nucleation time, so we can vary the density of precipitates, we can vary the growth time, so we can vary the size of the precipitates. And what we ended up with in this particular study is a huge set of samples with 5 orders of magnitude variation in the strain precipitate density from etching by varying the growth time from 0 to 16 hours. So we've got huge variations here on the vertical axis, that's density variation, and on the horizontal axis we've got huge variation in size. So we've got a big matrix of precipitates, and we characterised them by lots of methods, etching, TEM, and we did IR measurements to look at the oxygen disappearing at the same time. Okay, and then we did some lifetime measurements, and this is what we got, and we got a very characteristic lifetime curve, and pretty much everything we do, certainly in the P-type case, everything we do to these materials ends up with the same injection response. So this is the N over P formulation I talked about earlier. This is the residual lifetime, so it's corrected for things we know about, like the Auger, and the band-to-band. We get these 2 defect-like injection-dependent lifetime curves. So every time we process a P-type sample, whatever we do to it, we end up with this injection response. We end up with one centre here, which we call defect 1, another centre here, which we call defect 2, and if you add them together, you always can match the experimental lifetime curve. And we've done this with hundreds of samples. The first comment is that we know that this is not a single defect. So if we had a single defect, we'd have one straight line. We clearly don't have a one straight line, we have at least 2. And so the first conclusion we drew is that actually oxygen precipitation creates more than one defect. We then did lots of more experiments. We varied density, for example, and you get a whole family of lifetime curves. So these all have the same doping level, about 10 to 15, but these have different concentrations of oxide precipitates. So this black one has about 1/10 to the 10 per cubic centimetre, this one has 2/10 to the 10, and this one has 7 times 10 to the 10. But in all cases, the injection response is pretty similar. And we could always fit it with these 2 centres, which we call defect 1 and defect 2. We've done the whole thing again with N-type. This is a slightly different plot. This is residual lifetime, we call it. So we factor out the things we understand. So we factor out the intrinsic lifetime, and we plot this time, this is N-type, so we do it the other way around. The details are in the paper I mentioned earlier. But basically, this plot has different doping levels. So this yellow one is 10 to the 12, this red one is 10 to the 13, and this green one is 10 to the 14. And the density of precipitates is pretty similar in each case. And you see that you get lifetime which depends strongly on doping. We can put all this together and we can apply the approach that I talked about earlier, and we can extract the Shockley-Reed-Hall parameters. And so we bring up the usual equation. All we do is we fit straight lines to the data, one going one way, one going the other way. We do a manual fit. We get the gradient and the x tends to 1 intercept out, and we stick them in the equations, and we do a plot versus 1 over the doping level, and we use this to extract the defect parameters. Okay, so as before, the intercept gives us information on the capture cross sections, and the gradient of this plot gives us information on the energy levels. And we do this for all our samples. And here we've got the plots for p-type and n-type, and we have 2 defects. We have defect 2 on the right and defect 1 on the left, and we get perfect straight lines for both cases. And this really captures the physics of the recombination process here. We always get straight lines on these plots, which means that the Shockley-Reed-Hall parameterization is valid, and we can extract out, with a bit of work, the ratio of capture cross sections and the a term related to the energy level position of the 2 defects. And the values are on the screen. Now we can do some more things as well. We can do temperature dependence, and that can isolate whether the state is near the valence band or the conduction band. And it turns out that actually 1 defect is near the valence band, 1 is near the conduction band. We can even work out the activation energies for the capture coefficients from the temperature dependent lifetime measurements. So basically what we have here is a complete parameterization of lifetime in oxide precipitate containing silicon. And we can go a bit further than this. We can go and look and characterize things in other ways and combine them with lifetime data. So on the next plot, we've got some TEM data combined with lifetime data. And this is quite remarkable. So in this sample on the left, we have precipitates that look like this guy. This is a strained precipitate, about 50 nanometers in size. And the sample on the right, we have strained precipitates surrounded by 2 microns or so of stacking fault. And in both cases, the injection response is exactly the same. The value of lifetime is a lot higher when the stacking faults are not there, but the form of the injection response is exactly the same, depending on whether or not we've got stacking faults around the precipitation. That's quite remarkable. So these stacking faults introduce more centres, but they introduce more of the same centre, which we were quite surprised by when we first got this conclusion, but we've got reasons to understand this, which I'll go on to later. We can even look at these unstrained precipitates, these so-called ninja particles, and we can infer their densities by further processing the samples later. And so if we take a sample and fully convert it, all its precipitates into strained ones, we can work out the unstrained concentration by measuring the strain concentration at a given time and taking that away from the final value. So we've got a way of getting the unstrained precipitate density, and we can work out the recombination parameters of the unstrained and the strained ones. We find that the injection response is the same, but the strength or the density per precipitate of recombination centres is less in the unstrained case than in the strained case. But the form of the injection response is always the same. So we were puzzled a bit by this, and we first thought when we did this, when we published this, and we thought that the recombination activity was actually dependent on the density of precipitates. We now know this not to be correct because we've done additional work, but at the time we thought that the strained precipitate density was the key parameter in terms of the density of recombination centres, and these plots are approximate because the errors in the oxide precipitate density measurements are quite large, but actually you do get approximately linear trends. We now know this not to be right, and I'll come on to that later. So we did some experiments to work out what the mechanism of recombination was. And so rather than just doing the standard processing, we used vastly different thermal treatments. And what we did is we used a really wacky thermal treatment from device processing. We used about 10 high temperature steps between 900 and 1175. We created samples with vastly different precipitate sizes, but the same density. And so here you can see two curves. One is for a process we call process A. This is for process B. Process A is the normal process. Process B is a crazy process designed to make very large precipitates. The density of precipitates is the same roughly the same in both cases, but the size is much bigger in B than in A. And so what we did is at the same time we correlated IR loss data with the lifetime data, and this is on the next slide. And from doing infrared spectroscopy, we could write down simple equations to link the lifetime parameters to the size of spheres or platelets made out of oxide precipitates. So just doing a 4/3 pi r cubed argument, saying that the states are evenly distributed around a sphere or around a platelet, we can work out equations for the expected lifetime variation with IR loss data for the oxygen concentrations. And by doing this, we found a really good correlation with the surface area of either spheres or platelets. In fact, the correlation is pretty good in both cases. But we found that actually when we varied the size, we didn't get a correlation with density. So these top plots are the standard plots for density versus recombination center density. There's poor correlation, whereas if we go to a surface area argument and correlate that with the IR loss spectroscopy data, we can actually work out that there's a good correlation with IR and surface area of spherical or platelet precipitates. We can't actually say which, but it just shows the power of injection-dependent lifetime analysis. I said that we did some work on the mechanism of all this, and this is even more remarkable. If we contaminate the samples with iron, we find that the injection response doesn't change. So these samples have been contaminated. This one is uncontaminated on the left. These three on the right have been contaminated with iron, high purity iron, at different temperatures. And so by changing the contamination temperature via the solid solubility of iron, we can control the amount of iron in the material, and we can measure using lifetime measurements to measure interstitial iron concentrations. We can measure how much iron is not in the bulk, and so how much iron is therefore at the precipitates, and we can correlate this with the lifetime data. And the first thing to note is that actually the uncontaminated case has exactly the same injection response as the contaminated case. Now the lifetime goes down with higher contamination temperatures. This one on the right is very low, down to 3 microseconds. On the right here it's very high, it's up to about 500 microseconds. But the form of the injection response is the same whether or not we've contaminated it with iron. And here's another set of plots. We've taken the same wafer, cut it up into bits, and contaminated it with iron at different temperatures. And the injection response is largely the same form, but the density of centers depends on the contamination temperature. So how much iron goes in determines the density of recombination centers. And this is quite remarkable. And so we can correlate the state density with the iron loss to precipitates. These open symbols here are the solubility of iron in silicon, and these closed symbols here are the values of iron we measure in our samples. And so when we've got oxide precipitates, we always get lower iron in the sample than you get from an oxide precipitate free sample. And what we do is we assume that the iron that should be there from the solubility has gone to the precipitates. So if we contaminate at say 800, we should get say 310 to the 12 of iron, but actually in some samples we measure in the bulk around 310 to the 11. So we assume that that difference has gone to the oxide precipitates. And it does that during cooling. We've changed the cooling rate and we can work that out. And so what we have is a correlation between recombination strength of a precipitate and the iron loss to a precipitate. And we get these nice linear correlations here. And so what this says is actually the recombination strength of the oxide precipitates depends on the amount of impurity segregated to it. And that explains quite a lot. That explains why the iron is not makes no difference to the form of the injection response. it explains why the extended defects around the precipitates make no inform either. The stacking faults, actually, if they're clean, shouldn't be recombination active. But if they're decorated with metals, they will become recombination active. And so the metal decoration will be gives the same injection response. It explains why the ninjas have the same injection response as the strained precipitates. So we think basically that a lot of, certainly in our samples, a lot of the recombination activity of the extended defects are due to segregated metal impurities. And you can work out roughly how many you would need at each precipitate. So if you had an uncontaminated precipitate, so I think the point is we can never actually get an uncontaminated precipitate. If you look at the recombination activity of the uncontaminated samples, you do a calculation from the contaminated samples and work out roughly how many iron atoms you need per precipitate. You only need about 15 iron atoms at each precipitate to get the recombination activity we see. And even in the highest purity Joukowsky materials, you're going to have enough iron around, or metals of another kind, to get that kind of level of contamination. So we think that the whole, certainly in our case, when we've got silicon nitride passivation on the surfaces, we get hydrogen in the material. We think that any dangling bonds are going to be passivated by the hydrogen, and so the residual recombination activity of the precipitates is likely to be controlled by metals. Okay, and if you make that assumption, you can get the absolute values of the cross sections out. We published that in the paper at the bottom. Okay, the other thing you can do, we've got a really neat way of measuring iron at the precipitates. So we can do things like study the competitive Gettering in the material. So if you've got a strained particle in the material, it might be assumed that the metal impurities that in the material will end up at the strained particle and not go to the phosphorus diffused Gettering centre. So we've done competitive Gettering experiments where we've tried to getter metals away from the oxide precipitates. And this is the first experiment we did we did the Gettering at ISFH, but we took this black curve, which is pre-Gettering, we phosphorus diffusion gettered it, and we monitored the lifetime, and we also monitored the bulk ion concentration. And this is the interesting result down here, the bulk ion concentration. What we find is that the bulk ion concentration goes down during the phosphorus diffusion Gettering, but the density of recombination centres goes down as well. So what this tells us is that the iron that was in the bulk isn't gettered to the oxide precipitate, it's actually gettered to the phosphorus diffused layer. So we can study both iron at precipitates, because we've got a measure of that using the recombination parameters, and we've got a measure of iron in the bulk, and so we can study the ratio of iron in the bulk to iron at the precipitates. The other thing we did is a set of experiments on phosphorus diffusion, intentionally contaminated samples. So we took some precipitates, we contaminated them with iron, and then we tried to clean them up. And what we found actually is that in a lot of cases we could do this. So this is a contamination temperature, this is a density of centres, and what we find is that actually before Gettering we've got these black points, after Gettering we get these red points. And so if there's iron in the material, we can generally getter it away from the oxide precipitates to some extent. But there does seem to be some residual recombination that stays there, so perhaps there's more stable sites around the precipitates that will always retain iron, but certainly a lot of the iron that's at the precipitates at the high temperature contaminations can be removed. So the picture we've got here is actually that iron comes off the oxide precipitate, the extended defect, and this little animation shows what happens during the Gettering. So we get iron at the precipitates, and a lot of it comes off and is gettered away. And so we can get all this out from injection-dependent lifetime data, which is quite neat. Okay, so that's the second part of the talk. That's saying that oxide precipitates can be understood really clearly using injection-dependent lifetime data. Combining it with things like TEM and IR spectroscopy, you can get a lot of information out, a huge amount of information that you might not have thought is possible from just injection-dependent lifetime data. We can fully describe the system. We can write down parameters which will model the lifetime in oxide precipitate containing silicon. We understand N and P type. We understand the role of extended defects, the role of metal impurities. It looks like we can get iron away to most extents from oxide precipitates, and so we've got a good understanding of that system now. In the third part of the talk, which is essentially the final part of the talk, I'm going to talk about something totally different, which is not using injection-dependent lifetime measurements per se. It's about internal Gettering in multicrystalline silicon. So it's on a similar theme. It's about lifetime, bulk lifetime, but we're moving from high lifetime materials into low lifetime materials. Right, and so you're probably all familiar with the idea of Gettering. Generally, we have two types of Gettering. We have external Gettering and internal Gettering. External Gettering is things like phosphorus diffusion, boron diffusion, aluminium Gettering, possibly soil damage Gettering, all kinds of surface-related Gettering. We also can have internal Gettering. And by internal Gettering, we mean moving impurities to regions within the material, such as dislocations or precipitates or grain boundaries, and tying them up there. So what we're trying to do is, rather than externally getter the metal impurities, we're trying to internally getter them. So we process the material to get the impurities to cluster in some way, we don't really know where, and get the overall lifetime to increase. So our take on this is work I started at Oxford. Our take on this was to do it at low temperatures. High temperatures are expensive, and you can actually get more contamination at high temperatures. If you go to low temperatures, the solubility of the transition metals is very low. So we're working below 500 degrees C, and at these kind of temperatures, the solubility of transition metals, this is copper and nickel, but iron is right down here, it's 10 to the 7, something like that. Solubility is essentially negligible. And so we can do these experiments. The idea was to do them like you would toughen glass. You take your solar cell, you anneal it for 3 days at some low temperature between, say, 300 and 500. You get the metals to redistribute and overall end up with a higher cell efficiency. And to some extent, this has been successful. So you might be familiar with some prior work on this by the ISFH group, by Raphael Crane and Sandra Herlofsson and Jan Schmidt. They did some work on internal Gettering and multi, and they appeared to present a very complete picture of what went on. We don't think it's that straightforward. So what these guys thought is that you can take multi. This is interstitial ion concentration. This is annealing time. These are different temperatures, 300, 400, 500, low temperatures. You can anneal the materials, and the iron drops off nicely in a way that's consistent with the transport of iron. The activation energy here for the process is similar to the diffusion coefficient of iron activation energy. So they presented a very straightforward picture of what goes on in multicrystalline silicon at low temperatures. What they didn't do in their experiments was actually talk about lifetime. So they did these experiments where they did the internal Gettering, the iron went down. They didn't actually say what happened to the lifetime. That's probably because they couldn't say what happened to the lifetime because of their methodology, because they were using silicon nitride as a surface passivation layer. And when they were annealing, probably what was happening is that the surface passivation was changing, and also hydrogen was diffusing into the material and changing the lifetime. So it was unclear, probably, when they did their experiments, whether the hydrogen from the silicon nitride was changing the lifetime or whether the motion of impurities was changing the lifetime. So we want to actually answer the question, what happens to lifetime during this process? We also want to look at the role of hydrogen, because this is quite an interesting topic in many areas of silicon materials at the moment. There are some other studies in terms of low temperature Gettering. This famous one by Marcus Rugno, he took a load of essentially completed cells that weren't quite completed, but after emitter formation, he annealed the cells at different low temperatures, and he actually found he could get an improvement in cell efficiency by low temperature internal Gettering. Also, there's some work at ANU by Anyao Liu and Dan MacDonald, where they did internal Gettering after oxidation. So they did the surface passivation by thermal oxidation. Now, actually, the devil's in the detail with all these experiments. So the Hamlin work was using silicon nitride. There was a hydrogenation risk there. The Renewable work was good, but it was done on completed cells. So you had a combination of internal and external Gettering because you had an emitter on. The ANU work, again, was good work, but it was done after a high temperature oxidation. And so starting the process actually to do the passivation changed the distribution of impurities. So actually, I don't think there's a very complete study of internal Gettering in multicrystalline silicon. So what we aim to do is try and work out what's going on exactly. So the devil's in the detail. I've just said this kind of thing, but when you're doing studies of internal Gettering, doing the studies like this, the surface passivation can change the system significantly. So obviously at high temperatures that's an issue, but we've also found that when you do these experiments, even at low temperatures with 350 silicon nitride, or even lower temperatures for ALD, Al2O3, you do get changes in lifetime just due to the surface passivation. Now those changes arise for two reasons. One is thermal. The thermal processing moves the impurities around. The second is hydrogenation, which probably occurs to some extent in most dielectric deposition-based passivation schemes. The other thing is that the surface recombination velocity can change when you do the annealing if you leave the passivation on, but that's a secondary issue. So what we're trying to do is understand properly what's going on in internal Gettering. So, of course, the other thing you've got to bear in mind is when you do the experiment in the cell process, there's no good, so you have to do the Gettering at a time which is not going to be reversed by later steps. So this is a cell process, as you all know. You could do the Gettering here on the as-grown wafers. You could do the Gettering here after the phosphate diffusion. You could do the Gettering here after the cell production, essentially, with the metallization. You could even do it on a module if you wanted to, but that's probably not going to work. But there are different stages at which you can do the internal Gettering. And so what we're trying to do is experiments to isolate which stage is important. And so we've got what we call experiment 1, 2, 3A, B, and C. I'm going to talk about 1 and 2 because they're complete. We're also doing experiments 3A, B, and C. It's a very important thing to work out where this should go, but I'll come on to that later. Okay, so this is our sample process. We want to make sure that we don't introduce hydrogen. And so the way we do this, we think, is hydrogen-free, and that's to use iodine ethanol surface passivation. You've probably seen this. It's very low cost. You can do it in your lab. You can buy a sandwich bag. You can buy some iodine. You can buy some ethanol, mix them together, and you can make lifetime measurements under this solution. Here's the process in detail, and you can anneal the process. The good thing is, though, that you can do this process every time you make a lifetime measurement. So my PhD student, Mohammed Al-Amin, has been doing this for the last 2 years on different samples. And what he's done is a complete study of multicrystalline silicon from different positions in the block. We've taken top, middle, bottom, and bottom wafers. We've characterized them by optical microscopy, essentially, dislocation density measurements, PL imaging, and we've done a full study of lifetime in this material. And so this is the winning result, really. This is the internal Gettering data. Here we've got the lifetime measured with the ion in the FeB state, and here we've got time. And what we can find actually is, this is on the as-received material with iodine ethanol passivation. And what we find is that in spite of the lack of hydrogen, we get substantial improvements by a factor of about 7 or 8 in bulk lifetime just by annealing the samples at low temperatures. So at 300 degrees here, the bottom wafers improve from maybe 5 microseconds up to about 30. Slightly higher temperatures get slightly better results. And if you go to higher temperatures still, you actually get slightly worse performance. Now the effect is complex. And so what I'm going to show is a few examples. And what we've done is we've actually monitored lifetime at every stage in the process. So we've got these nice movies, which I hope will work. And what should happen, these are different time steps, and you can see what's happening to the lifetime semi-in situ. So this is one wafer. And so what happens then, you take the as-grown wafer, the lifetime's generally bad. And what happens with annealing time at 400 degrees C is that the bulks of these grains start becoming good, and certain regions stay bad or even get worse. And we can also monitor, at the same time, we can monitor the ion concentration. So this is a map of the interstitial ion concentration, and it starts off the scale actually about 10 to the 13. But as the ion starts to reduce, we get bulks of the grains which become essentially ion-free, and you get certain clusters which become contaminated with iron. And so we can try and understand what's going on here. And this is all in the absence of hydrogen. So we can go on and look at what happens to lifetime. We can correlate the lifetime change with the change in interstitial ion concentration. And effectively in bottom wafers, where we've got high iron but relatively low dislocation density, we get a good one-to-one correlation between lifetime change and ion change. We do find, however, an interesting effect that wasn't expected. When we take a good wafer and try the internal Gettering, it actually gets worse. So this is in the absence of hydrogen. This is iodine ethanol, and it actually happens really early on. That the ion, so the lifetime, even after 5 minutes, crashes. In the absence of hydrogen, low temperature annealing kills the lifetime of multi. I don't think that was known before. So if you look at the as received wafer, in 5 minutes, it's pretty much dead. It does recover slightly with time, but it never gets much better than where it started. So what we've noticed here is that the hydrogen not being there has a huge effect on the lifetime, and I'll come on to that in the next set of experiments. So I've got to go a bit quicker. I'll skip that one. But what we have here is a really interesting effect. At 500 degrees C, when we don't have hydrogen in the system, with iodine ethanol passivation, the low temperature annealing appears to release iron from the bulk, into the bulk. So if we monitor the ion concentration with annealing time at 500, we always get an increase in interstitial ion concentration. So it's like iron is bleeding out of some defect into the bulk. Now, we get completely different results when we have hydrogen. So we've done the same experiments with silicon nitride surface passivation done at ISFH, and I've plotted here the ratio of lifetime to the starting lifetime, because they're slightly different samples. They're sister samples at each position, but they're not sisters between the silicon nitride and the iodine ethanol. The red points are the iodine ethanol, the black are the silicon nitride. And what we find is that, say for the good wafers at the middle bottom, iodine ethanol kills the lifetime with annealing at, say, 400, whereas silicon nitride increases the lifetime. And so we get very different behaviour depending on whether silicon nitride is used or iodine ethanol is used for surface passivation. And we explain that in terms of hydrogen. We have no direct evidence for hydrogen being involved. It's very hard to measure low hydrogen concentrations. But there's a really big difference between the passivation types used. And this, again, is the iron. That's the lifetime. This is what happens. This is a direct comparison between the silicon nitride case and the iodine ethanol case. And the one on the left gets substantially worse by annealing, and the one on the right actually stays roughly the same. So the iodine ethanol eventually crashes, the silicon nitride stays the same. So it's like the hydrogen from the passivation scheme is stabilising a lifetime during internal Gettering. And there's also a lot of data on iron. And this is the really interesting thing, is that the iron concentration when you've got iodine ethanol surface passivation increases. When you've got silicon nitride surface passivation, it decreases. So the behaviour that Schmidt observed and Crane in their internal Gettering paper was in silicon nitride passivated samples, and we roughly agree with them in spirit, if not exactly in quantitative detail. When we do silicon nitride passivation, the ion concentration decreases, but without that passivation, we find that the ion concentration actually goes up. Okay, and here is a comparison with Crane. We actually find that we don't really agree very much, because they didn't use sister wafers, we use sister wafers. We actually find that there's a peak of performance at about 400. 500 doesn't actually make it any better, it makes it worse. But we get a big difference between iodine ethanol and silicon nitride. So I'm running out of time, so I'm just going to finish the talk by giving a plug to another piece of work that's being done in my group, and this by Nick Grant. This is about float zone stability. There's a paper that's about to come out in the next probably 24 hours in Physica Status Solidi Rapid Research Letters about what happens to float zone silicon under annealing. So one might think that float zone silicon is the best silicon you can get, and if you're doing your passivation studies, you might use float zone. This is not actually the case. So we've done, well, Nick did when he was at ANU, he did a lot of bulk lifetime measurements on float zone material from different manufacturers. Now the lifetime can be very high, can be 10 milliseconds, but actually the lifetime of float zone is not stable. And so what you find is that at temperatures like 400 to 800, you get a big crash in lifetime. And you can see that in terms of the distribution of interstitials and vacancies. You can understand that in terms of this X-ray tomography image, and you can understand this, like in the oxide precipitate case, it's to do with vacancies and interstitials and them giving rise to recombination in some way. So in summary, lifetime's important. Give it a go. Give the injection-dependent measurements a go. Try analysing lifetime as a function of N over P and not just delta N. Oxide precipitates are important, as well as a boron-oxygen defect. Low temperature Gettering is complicated, but can, in as-grain material, give rise to a substantial improvement in lifetime. And be careful with passivation. The devil's in the detail on that. The different passivation types for internal Gettering make a huge effect. So with that, I'll finish, and I'll be around outside because we've got to get out of the room. So I'll take questions outside. Thank you.